asymptotic analysis and big O. These concepts are an application of limits into wider mathematics. Asymptotic analysis uses limits to show that as functions approach infinity, the constants in them become insignificant. Big O then takes this concept and gives it an application outside of specialized mathematics in the world of computer science. There, it is used to calculate the relative complexity of algorithms. To begin, let's go over what asymptotic analysis is. Asymptotic analysis is defined as a method of describing the limiting behavior of a function as it approaches infinity. So in essence, the opposite of calculus, which looks at the limit as it approaches zero. This is exemplified by going through an example. Let f of n equal to n squared plus 12n, and let g of n equal n squared. In this case, f of n is asymptotically equivalent to g of n. Why is that, you may ask? As the function of n, as f of n approaches infinity, 12n becomes insignificant in comparison to n squared. Let's look at how these two functions grow. On each row of the table, we have our two functions. Each column tests a different value in the functions. The first value we'll try out is 2. As you can see, f of 2 is 28 and g of 2 is only 4. If we take the difference of the two functions, we find that f of 2 is 600 times bigger than g of 2. Now let's substitute a bigger number, say 16. Now f of 16 is equal to 448, and g of 16 is equal to 256. The gap between the two functions has dropped from 600% to only 75%. This is a rather drastic decrease. If we take another step to a larger number like 512, we can see that f of 512 is 268,288, and g of 512 is 262144. The difference between these two numbers is only 2.3%. And if we take a further step to 4096, we see that the difference between the two functions becomes as low as 0.293%. We can see that as the value of n approaches infinity, the difference between the two functions becomes smaller and smaller. The limit would be 0 as n approaches infinity. This is the main idea of asymptotic analysis. Asymptotic analysis can be formally defined as such, with a limit. F of n is asymptotically equivalent to g of n if the limit as n approaches infinity of f of n over g of n is equal to 1. This shows that limits are an essential part of asymptotic analysis. Now that we know this basic concept, let's move on to asymptotic notation. Asymptotic notation is used to describe the limiting behavior of functions as asymptotic analysis defines it. Asymptotic notation is not only a notation in itself, but a collection of notations. The most common asymptotic notation is big O, one of my topics. Let's take a deeper look into it. To formally define big O, first we need to define a few constants. We have f of x, g of x, x0, and m. F of x and g of x are the same as the functions used before. M is defined as a constant that can be multiplied by g of x to make it bigger than f of x after the point x0. x0 must be greater than 0 and is defined as the point where m times g of x will always be bigger than f of x. Using this, we can formally define big O as f of x is equal to the big O of g of x if f of x is less than or equal to mg of x for all of x above x0. This also defines f of x at most to be some constant multiplied by the function g of x past the point x0. This can be observed in this graph. On the graph, the blue line represents m times g of x, and the red line represents f of x. As we can see, before the value of f of x, the two lines are intersecting each other frequently. However, after the point x0, m times g of x is larger than f of x at all times. To find the constants of this equation, all we need is f of x. Let f of x be 12x cubed plus 7x squared plus 3x plus 4. G of x has to be asymptotically equivalent to f of x, therefore g of x is equal to x cubed. To find out the constant, c, we will need to find an equation that's bigger than f of x. Let's just take all the constants in f of x and make them asymptotically equivalent to g of x. A new equation would look like this. M times g of x is equal to 12x cubed plus 7x cubed plus 2x cubed, which would simplify to 21x cubed. Now, since g of x is x cubed, therefore m of x has to be 21. M has to be 21. However, when x is 0, f of x would be equal to 4, whereas m times g of x would be equal to 0. This would mean that f of x is larger than m times g of x at the point 0. This changes when x is equal to or more than 1, where m times g of x will always be larger than f of x. Therefore, m is equal to 21 and x0 is equal to 1, as x0 is the point where the function becomes larger. Now, how is this useful in any way, you may think? Big O has applications in computer science. There, it is used to show the relative representation of complexity in an algorithm. To understand this sentence, first we need to understand what an algorithm is. An algorithm is a set of steps, or otherwise a procedure, for a computer to execute in order to produce some result. Algorithms take inputs, execute the procedure, and then give outputs. Big O is used to calculate the worst case running time of an algorithm as the size of the input increases. Let's go through a few searching algorithms and calculate their efficiency. The first one we'll look at is linear search. Linear search is a very basic algorithm. It's how you do it if you didn't have any idea where to look first. It works as following. Step 1. Check the value at the point. Step 2. If the value matches, exit. Step 3. Move the pointer 1 to the left. This repeats over and over until we have found our value. Now, let's calculate the worst case running time for this code. What would this scenario look like? We would need the value we are looking for to be the last value in the list, so we need to look through all of the values in the list to find it. This would mean we would need to go through the list 3n steps to get to this value. As we know from asymptotic equality analysis before, we can simplify this to O of n. Let's look at a better algorithm. Binary search is a recursive algorithm. This means it runs smaller versions of itself in itself. It's much more efficient this way. Binary search only works on ordered lists. If you were to choose a value, the search will go from the center of the list and check if the value is in the next half of the list or the first half of the list. This then calls binary search in the half of the list containing the value. This would result in a big O of log of n. Here is an image to illustrate better how this works. Now let's go through its steps. Step 1. Go to the center of the input and split it. Step 2. If the item is present by itself, exit and return this value. Step 3. Run binary search on the side containing the value if it has not already been found. We can see from the complexities of these two algorithms that binary search is incredibly efficient in comparison to linear searching. We can convert this into commands per line, commands per algorithm in worst case. Let's look at a table to exemplify this. We can see that for each efficiency that exists, some algorithms are rather undesirable. Even as these numbers are incredibly large, modern computers would be able to execute them in fractions of a second, as they are able to perform 10 billion operations per second. However, the value in the lower left corner would take a few years to run, even on the most modern computer. Therefore, we should always strive for the lowest big O possible when making algorithms. Thank you for your time. I hope you learn more about the application of limits in the wider mathematics and even in a general sense.